Okay, so we're going to start at basic forces regarding reactions on beams determined by their loads. So we're going to be looking at moments, which effectively moment equals torque. Give you a bit of an idea on that. If we say had a spanner, and then in that spanner we had a nut, and if the spanner was this small, we would maybe require X. Let's put Fx, force X. We need a force with, it's an indeterminate amount is X, but it doesn't matter at this stage. So we need a force of X to turn, and let's say X equals 10 kilonewtons to turn this nut with this spanner. If we had effectively, let me see if I can draw the same spanner but only twice as long. What a lovely spanner this is. So there's our nut again, same size nut, but now what's changed is the value of X. So on this term, because it's twice the distance, so X equals 5 kilonewton force, because obviously we double the distance. So the moment is actually here. Well, no, let me just come back out of that. That's incorrect. The moment would be here, obviously the center. So the axes of rotation, so let's put that in, is the axis of rotation, and it's also, we could say that's a pivot point. And in some instances, like if we've got a seesaw type, this also applies to this point here, but we could also say it is a fulcrum. A fulcrum is a pivot point, or the axis of rotation, which is going to be at this point here. And the idea is it's obviously a force here times distance. So the distance in this case might be, let's say 10 meters, and a force of, let's say, F equaled 10 kilonewtons, excuse my phone, 10 kilonewtons. Therefore on this side, if we halve the distance, what do you think is going to happen? So if we say that's 5 meters, F equals question mark. Okay, what do you think that might be? So I'm going to do an example of that in a second or two. Let's park that for a second. Let's park that for a while, and come back to it. So you get the idea with the spanner. It's twice the distance. So we've got more torque. We've got more moment through the axis of rotation at this point here, at the center of the nut. The same again here. This is the point at which the rotation is going to happen. Okay, let us let's take another blank page. I might come back to that shortly. So what we need to do is let's draw an example here. So we've got our fulcrum, we've got our seesaw there, and we can say, let's say we've got force 1, okay, and we've got, so that's at this point here to this point here is D1. Okay, so F1 times D1, so F1 times D1 is equal to, if we put a force here, F2, and then, oh, let's get that a little bit nearer because we're trying to solve the problem of, let's say, so it's half the distance, so F2, okay, so we can say F2 times D2, but we've not given them any numbers yet. We don't need to, or we can simplify that even further to say F2 D2, so F2 times D2 minus capital F, F1 times D1 equals 0. So as long as everything adds up to 0, that's in equilibrium. All right. So let's take this a little bit further. Create another word there, and let's draw our seesaw again. So there's the seesaw. There's our pivot. And we're going to look at mass. Okay, we're going to look at mass. So the first thing, if we go back to that original one there that we've just done there, if we could just highlight these two here, highlight this and this. What we need to understand about axes of rotation is something called clockwise moment. It is effectively moving, but clockwise moment and anti-clockwise moment. You may even see in some books or online videos that it's counterclockwise, anti-clockwise, counterclockwise. It's pretty much the same thing. Let's just go back to that a second. So what we can see, we can see that this force here is a pulling force, and it's rotating in that direction. So an anti-clockwise movement, and this one is a clockwise movement. So this then supports this idea that F2 times D2 minus F1 times D1 equals 0. So all the forces add up to 0. Now we can see, I've just noticed that I haven't put D2 in, my mistake. So we can see that the forces would be different because the distances are different, but we still got balance, we still got equilibrium. So if we take a bar, a beam like this, and we apply a load in the center, force, effectively what that beam wants to do, as we know, it's going to put it into compression. It's a slightly exaggerated version. So let's put our force, let's put our beam, and let's also, you've got a neutral axis through the center of the beam, and that's in equilibrium, it's at 0. Obviously now things are starting to change because we've got no longer a neutral axis in the center. We actually have in this sense. It's going to be different if we applied a different type of force, an angular force, but that is still 0. But the difference now is that if the molecules in this beam were represented like this in a state of inertia, in a state of equilibrium, we can see here that because of the compressive force, all of the molecules are being crushed inwards. That's the compressive force. And then likewise we've got the torsion on the underside, like so. and we've got a situation where, let's just write that in. So we've got compression here, and on the bottom we've got torsion because all the molecules are being pulled away from each other. Torsion. Okay, so that's what's happening when we apply a force in the center of that beam. Now let's get rid of this and talk about clockwise and anti-clockwise movement. So let's suppose in them the force in the middle of this beam is acting. What the force actually wants to do is this. It wants to break the beam in half, doesn't it? That's what it actually wants to do. And this is where it could get slightly confusing in terms of the moment. Ordinarily, you would say that this is going down in an anti-clockwise moment. Therefore, this one, sorry, I'm giving the answer away there. In a clockwise moment, because obviously we want it's going down as a clockwise moment, and then this is tumbling to the ground in the opposite direction. So this is anti-clockwise moment. So it's moving in anti-clockwise, but that's not the case when we determine moment on a bar, because the idea of moment is that we know that for every action there's an opposite and equal reaction in terms of force. Otherwise you would need an infinite amount of force for that not to happen. So this is true. This is actually true if the bar did break. Then obviously this part here would move down. It would go down in a clockwise manner, movement, motion, moment. That, of course, it would. However, when we start calculating stress and bending moments and shear on beams, let's just complete our beam back again. What it's actually doing, if we just draw it again, like so. Now let's presume that the bar is in equilibrium, so the force down is equal to the force up. Okay, so let's say F equals X and FR, which is resistant force, equals X. So they're both the same. It's a resistant force. So whatever force you're applying down at the center of that beam, it's maintaining its equilibrium due to this. This half of the beam is the resistant force. So it's an anti-clockwise moment. And equally, this one is pushing back up in a clockwise moment to maintain equilibrium. Okay, so let's take a view like this. If we draw the same beam and we've got a force down, force equals X, and then we've got this here. We've got an anti-clockwise moment and a clockwise moment there. So both of them would equal FR. So it's a resistant force. It's the resistance to that beam. So the force down wants to break the beam in half, but because it's in equilibrium, we've got the anti-clockwise movement on the left here pushing back up, and then obviously on the right hand side we've got the clockwise movement pushing back up there. So it maintains equilibrium on both sides of that beam, so it stays straight effectively. So that's where it can be confusing. So even though it looks like don't look at the beam as if it's going to break, so therefore it's the opposite way round, as in the piece on the left here would go down in that if it were to be broken, and obviously the right would go down that way. So it would be obviously true to say that the one on the right is going down in an anti-clockwise moment and not a clockwise movement. But what we're doing, we're calculating equilibrium. So this is obviously over here. This is the equilibrium here. We're trying to maintain that. So that's the resistant force. Okay, so taking a look at some simple examples, a couple of examples of our seesaw and forces acting upon this. Let's suppose for argument's sake, we've got a number of forces acting in different directions. So we saw in one of these examples, I think it was this one, where we could see that this force here, this one, is acting in an anti-clockwise manner because it's trying to counteract this force here, this one. Okay, so both of these need to be balanced out so that the seesaw stays the same. So what you're getting here obviously needs to be counteracted with this one. Okay, but let's make it a little bit more difficult, and then we'll do an example. So let's suppose in them we've got let's say we've got, let's draw the forces in it. We've got a force here, let's say that's 6 kilonewton. Let's take another one here. Let's say we've got 42 Newton. Let's say we've got one around about here. Let's say that's 8 Newton. And then let's add a force over here. In fact, let's do this a different color because in fact I should really have done that in a different color, and I'll tell you for why in a second. So the ones in the blue, okay, the ones in the blue are clockwise movement or clockwise moment, and the ones in the red are going to be anti-clockwise moment. So let's draw one of those. Let's draw one here, and let's say that was 7 Newton. Let's draw another one here from there, and let's say that's 8 Newton. And then we draw another force over here, and let's just call this F. We don't know the value of this force. Okay, we don't know the value of this force. Now what we need to do is put some distances in. So let's say 6 kilonewton, let's say this is at 9 meters. This one is 7 meters. This is, let's say, 2 meters. And then we've got this distance here, so the 8 Newton from the central axis, the axis of rotation, let's say that is 4 meters. And then we've got F, let's say F is 9 meters. Okay, so we've got 2 clockwise moments, the 6 and the 42 newtons, and then we've got the 8, but we've got at 9 meters we've got an unknown force, but we need to find out what that is to provide equilibrium. Okay, so let's calculate the clockwise moment first. So remember, it's force times distance, capital F and a lowercase d. That's usually the way it's put. Well, it is the way it's put. So we've got 6 kilonewton times 9 meters plus 42 kilonewtons times 2 meters, and that is equal to, let's move this over here a second. So that's let's do a black equals there, and then we've got anti-clockwise moment. Sorry. So we've got our force here, 7 newtons times 7 meters, because obviously this here is going in an anti-clockwise manner. So is this one. It's going in anti-clockwise, all the anti-clockwise forces. So we've got 7 kilonewtons, times 7 meters plus, so we've got 8 newtons, this one here, 8 newtons, so 8 newtons, correct, kilonewtons times 4 plus we've got F times 9, but we obviously still don't know what F is. So let's do the maths on that. So we've got 6 times 9 equals 54 plus 42 times 2, which is 484. And that must equal 7 times 7 is 49. Oops, so there's a 49 plus 8 times 4, which is 32, plus F times 9. Let's just put that in there so we don't confuse anybody. So 54 plus 84 is 138. So that's the total sum of forces in the clockwise moment. And that equals, so we've got 49 and 32, so that's 81. So we've got 81 plus F times 9. So we go 138 minus 81 plus F9 equals, so we got 38, 57. Let me just double check this. I'm going to make a fool of myself. So 138 minus 81 equals 57. So that equals 57 plus F9. Therefore, we simply 57 divided by 9 equals, so F therefore equals 6.33 recurring kilonewtons. So what we've just done there, we've just simplified the equation to find out what F is, and F in this case is obviously the force needed. Okay, at this point here, we need 6.33 recurring kilonewtons to maintain equilibrium. So that's about the total sum of forces in a clock. So the total sum of clockwise moments must add up to the total anti-clockwise moments, okay, for it to be equilibrium. Obviously, if it was the case that it wasn't 6.33 and we got it wrong, obviously we'd have a rotation again through the axis, the axis rotation through the pivot point, or in this case a fulcrum point. Okay, so if you want to just try doing I don't think I need to do one. In fact, what I'll do is I shall create one more for you, and let's see if I've got one wrote down for you there. Let's try. Right, so let's go for this one. I'll give you one to do, and you can work it out yourself. Any problems, just let me know. So let's just say we've got, so let's go blue again. So we've got 12 newtons, and we've got so this is, no, let's change that to, let's keep it simple. Let's go with the red because that's going to be an anti-clockwise moment. So let's say 12 newtons, and then we've got one here. Let's put one there at 5.5 newtons, and then we've got a pulling force here of 6 newtons, and then we've got a pushing force here of 7 newtons, and let's put one down here, and let's call this F equals question mark. if I just give you some distances, so let's say this is 9.5 meters. This one, let's say 6.5 meters. Let's say this is 4.5 meters. And then we've got one here from, obviously these distances are all from the axis of rotation from that point. So obviously 4.5 to there, and then obviously 6.5 to there, 9.5 to there. And then 7 newtons up, so we're at 7 here. Let's say that's 3.5 meters again from the point of rotation. And then finally we've got the last one there, and let's give this a distance of 8 meters. Okay, so give you a few moments to work that out, and then I'll show you the answer. So how did you do then? Very quickly, you've got the clockwise movements in the blue. So we got the first one here, 6, so force is 6, and then times distance 4.5. You can see that there, then that equals 27. We've got the second force here, force times distance shown here, and that's the answer to that. F, we don't know what that force is yet, but we do know what the distance is. So we've got that there, that remains the same all the way through. And the total for all of those added together is 51.5, which is shown over here, our equation. And then the anti-clockwise movements, we've got force times distance here, so 12.95. And then we've got, I've got this the wrong way around here. Let me just get this the right way around. Oh, I did have it the right way around. Sorry, I did. So it's 5.5 times distance, which is 6.5. And we can see that that's that one there. That's the one. So force times distance, and then we've only got the 2 on there. So 12 times 9.5 equals 114. 5.5 times 6.5 equals that. So that's our total there. So we take away 51.5 plus F8, which is over here, so 149.75, which is total sum of forces in the anti-clockwise movement, minus the known forces for the clockwise movement, which was 51.5 plus F times 8, which equals 98.25 plus F times 8. So simply 98.25 divided by 8, obviously because of that there, and that gives us the answer 12.28 newtons. So we can write up here then, changing the correct pen colour, F, and we can actually get rid of that. Well, now let's leave it in and just say that F therefore equals 12.28 newtons, which equals equilibrium. Okay, so now we're going to move on to simply supported beams, so we can look at what we determine as reactions, so reactions and loads. Okay, then in conjunction with page 49 of your student book, we're going to go through those two together. So we're going to look at, it says determination of support reactions for simply supported beams with point and distributed loads. So we're going to look at point load and distribution load, uniformly distributed load. And obviously, well, not obviously, but point load equals that symbol there. And then uniformly distributed load, which is always known as UDL, because it's a lot quicker, and that is that symbol there, and it'll give you something like 5 kilonewtons per meter, and you'll see that on a beam like that. Okay, so there's your UDL. You can see that on page 49. And to add something to the measure there, we could say there's a point load as well of 5 kilonewtons. Okay, so those are the symbols that we'll be dealing with in this next exercise. So very quickly then, well, not too quick, but there's what we call a this is called a free body diagram of a simply supported beam. Okay, and it shows in the book that it's arrows up like that. It could be done like that. It could be done. Let's get rid of them. It could be like that, so it's on two piers or abutments, or it could be. Let's get rid of that. Or it could be as simple as that there. Okay, so we'll just leave it at that for now. So we're going to use a point load here. We're going to say, let's say it is 12 newtons, and then we've got a distance of 3 meters and 3 meters. So a total span, the span is 6 meters. And then we've got our reaction left and our reaction right. Okay, so remember, force times distance. Okay, so force times distance. So the force obviously on there. So what we're going to do, we're going to look at the reaction at the left side here. Reaction left. In other words, what we're doing then, we're saying that this is where it gets a little bit confusing, because it's kind of it's like the anti-clockwise and clockwise moments where it's kind of the opposite to what you think is the logical way. So if you're calculating the right reaction, for instance, or let's say the left reaction, just here, this one here. What we're saying then is this here on this side, that's the axis of rotation at this point, because what we're determining whether this beam is going to go down. So in other words, that what's holding this up here is, let's supposing that it's not strong enough to support it, then this beam is obviously going to go down in an anti-clockwise manner. But obviously because of equilibrium, and we need to design something that's going to withstand the load, which is the 12 newtons, that's the load. So we need an opposite and equal reaction in that way also. So if we were to look at the left reaction, which is this one here, what we're actually saying is we're going to calculate the load at this point here. We're going to calculate this reaction, whether or not it's in this direction or that direction. So effectively, that's what all of that means. Now, so let's just get rid of some of this so we can. Right, so it's. In fact, how about I just rewrite the whole damn thing again? Come on. And let's make it nice and clear. I'm sure there's a quick way of doing this on this tablet thing, but I haven't found it yet. So there's our beam. Okay, simply supported, and we had a force there of 12 newtons, and then we had 3 meters and 3 meters. So the left reaction then, let's put those in, RL and RR, would look like this. So left reaction would be equal to 12 times 3, let me just put in brackets up here, force, distance. Remember, force times distance. So 12 times 3, and it equals 6, because that's the span. Remember, that's the distance there, times the right reaction. because don't forget both reactions need to add up to the total sum of forces, which equals 12 newtons. So we can simply say, therefore we can say right reaction equals 36, because that's what that is there. 36 divided by 6 equals 6 kilonewtons. And you can see that if we worked it both ways, then obviously it's going to be 6. The reaction here is going to be 6 kilonewtons, and also here it's going to be the 6 kilonewtons. So effectively, once you've calculated one side, okay, you take that away for the total sum of forces. So obviously 12 minus 6 equals 6, so that gives you the right reaction or the left reaction, whichever way you want to look at it. So let's take a look together then at the book, because going through the book, it's not really the most obvious. You do have to kind of read it a few times, and I can see that, you know, it can be a little bit confusing. So let's go through the example together in 1.25, fig 1.25. So it shows us a simply supported beam, like so, and then we've got 50 kilonewtons, we've got 100 kilonewtons, and let's put distance in. Oh, oops, a daisy. That's right. It is 4 meters, 4 meters, and 3 meters. And of course, we've got the usual resistant force, a returning force there. So the span in its entirety is 11 meters. Okay. I mean, there's a few ways you can write this. I mean, you see at the book there where it says the reactions equal the loads. So in other words, the reactions, so we've got reaction left, reaction right equals the loads. Okay. The left reaction plus the right reaction equals the loads, which in this case is 150 kilonewtons. Okay. So we know about the clockwise moment. So on here, obviously, we can say that on this side of the beam, that is an anti-clockwise moment, and on this side of the beam, this one here, that's a clockwise moment. That's supposing that you split the beam at 5.5 meters, okay, through the center. So obviously by moving the two loads, the 50 and 100, in different directions would have different effects on the equilibrium of that beam. Okay, so what we can do, so we know force times distance. Okay, so we can say if we're looking at we're going to look at the right reaction. Okay, so the right reaction is this one here. Okay, the right reaction. Now in the book, should we write it as the same way as the book? And then what I'll do is I'll give you another example and we'll go through that together as well. So in the book then it says the first reaction is 50 times 40. So right reaction equals 50 times 40. Sorry, what am I about 40? 50 times 4 there, and then we've got another force which is the 100 times a distance of 8 there, because what we're doing, we're saying from there to there is 4 meters, and then to the next force here, to this force, it's actually from there, it's 4 meters plus 4 meters, isn't it? It's 4 meters plus 4 meters, so it's 8 meters to this point here. If we just put that in lightly and then just say that that's 8 meters. Okay, that's why we've got that there. Okay, and then that equals obviously the span is 11, so it equals 11 times the right reaction. Okay, and we'll come back to that in a second, because it's simplified here when you say, well, obviously 50 times 4 is 200, and it's kilonewton meters, because we're multiplying kilonewtons obviously by distance meters, so it's kilonewton meters in that sense. And then we've got the plus, so the sum of 100 times 8, which is 800 kilonewton meters, and we divide all of that by 11, so force time distance divided by span. In this case the span is 11, so that's 11, and that equals as the book says, 90.91 kilonewtons. Okay, so we know that both reactions, so RL plus RR equals 150 kilonewtons. That's the total amount of load that we've got. So if we was to take away, if we take this reaction, okay, so let's do that in blue. So we've got a total load equals 150, and then minus our right reaction, which is 90.91 kilonewtons, then we're left with 59 equals 59.09 kilonewtons. Okay, so and if we add both of them up, again that equals 150. So obviously both reactions must add up to the total load. All right, total load can be a bit confusing, because I mean you could do it like this. If we was to get rid of all of this, all right, let's get rid of all of this, and let's do it in a different way. We can say that the reaction from this side here, whoops, I got my thingamajiggy on, there we go. Right, we can say from the left hand side equals 50 times 4 there, plus 100 times 8, and that equals 200 plus 800. Sorry, don't know why I'm doing that. What is going on there? Whoa. And then that obviously that equals 1000, and then divide that by 11 will give you, which equals 90.91, and then we can say 150 kilonewtons minus 90.91 equals 59.09 kilonewtons. There we go. So that's kind of a logical way to do it, but it's all about the reaction through. So if we're trying to understand the rotation through here, look, because this is where we're trying to determine whether it's going in this direction or that direction. Okay, so we're calculating this here. So the left reaction would be from there. Okay. Let me just, all right, let's go and do the other side. All right, there's our beam again. Okay, and then the left reaction, so let's put this, it might be helpful if we do that, kilonewtons, and then we've got 100 kilonewtons, a very scruffy one. Then we've got 4 meters, 4 meters and 3 meters. And there's our reactions again, just there and there. Right reaction, left reaction. So again, calculating from the left. So there we go, we're still on red. So right reaction equals, obviously we've got, now we're coming from this side, look, from there to here, so that's a distance of 7 meters, isn't it? 4 plus 3, that would be 7 meters, and therefore the force is 50 kilonewtons times 7 meters, the old bod mass there, and then plus, and then the shorter distance there from there to there is, so the force is 100 kilonewtons times 3 meters, like that. And then obviously we're going to divide that by the span, which is 11 meters. So when we actually run that, it's 59.09, and we already know that because when we add both reactions up, they're going to equal 150 anyway. So you could say 150 minus 59.09 equals 90.91 kilonewtons. So that's both the reactions. Okay, so now we're going to take a look at UDL. In fact, what I could do is I'll give you a quick example so you can work this one yourselves. Pause your video, and we'll come back in a second and see how you get on with this one. Okay. Okay, so how did you do? Looking at the example here, so we're looking at the right reaction. So we've got the force times distance, 11 times 2. Obviously that's this here, 11 times 2. Then we got 7.5 times 5, because obviously the distance from obviously from here to here is 5 meters. Then we've got 6 kilonewton force, and that is multiplied by 9. And then we've got 8 times 10, because obviously we've got 1 plus 4, 5 and 5 10, so we've got that there. And then all of that together equals 11.5, which is the span. So let's put that span in, 11.5 times the reaction on the left side. Okay, so putting that into old money, we've got the 22, the answer to obviously this here, plus 37.5, plus 54, plus 18. We divide that by the span, 11.5 meters. So our answer for the right reaction is 16.83. Okay, now the total loading force is, and we can see that here, the total loading force is 32.5. So total load is 32.5. And the right reaction there we've just determined as 16.83 kilonewtons. That's kilonewtons there. And then when we take that away from that, it leaves us the left reaction, which is 15.67 kilonewtons. And when you add both of those up again, it works out at 32.5 kilonewtons, which is the total, which is the total force. All right, next we're going to look take a quick look at UDL, and just to go through the worked example, which is on page 50, just to so we all get that thing straight. Okay, so the next thing we're going to do, as I say, we're going to look at the in the next video we're going to look at the UDL, look at a few more examples of perhaps point load and UDL together, and then we'll move on to bending moment and shear force diagrams. So that just leaves me to say, remember, answer the question and give the question back.